Hello and welcome to my talk, Boosting Fuzzer Efficiency, an Information-Theoretic Perspective. My name is Marcel Böhme. I'm a senior lecturer here at Manés University in Australia, and this work is in collaboration with Valentin and Sankil from KAIST in Korea. Now this paper is about fuzzing. But what is fuzzing? Fuzzing is a bug finding technique, and it's really simple. You need to generate inputs for a program, and you see whether the program crashes. It's highly efficient. It's so efficient, in fact, that it's being adopted in industry, and there are large efforts to integrate this into continuous integration so that commits are tested by not only static analysis tools, but also by fuzzing tools. And there are large efforts at Google and Microsoft, for instance, to fuzz not only their own products, but also open source products. So just for instance, in the last 3 years, Google found 16,000 bugs in their Chrome browser through fuzzing. But they also have this OSS Fuzz project where they onboard security critical open source projects, and they found 11,000 bugs in over 160 open source projects. So fuzzing is really efficient. But then again, what really is fuzzer efficiency? And how can we measure fuzzer efficiency? And how can we make fuzzing more efficient? So in this paper, we take an information-theoretic perspective. Specifically, we consider fuzzing as a learning process. Suppose you don't know anything about your program. You execute an input on that program. You see the behavior of that program for this input that you just executed. You execute another input on that program. Either you see the same behavior or you see a different behavior. When you see a different behavior, you learn something new about that program. So you gain some information. As you execute more and more inputs, you gain some information about the behaviors of the program. And the amount of information that you gain per input can be measured using Shannon's entropy. So in this paper, in this work, we develop an information theory for software testing and specifically for fuzzing. But it's generally applicable to software testing as well. What we do is we extend a statistical framework called software testing and analysis for the discovery of species, which borrows from biostatistics. And we accommodate mutation-based fuzzing in addition to generation-based fuzzing. So in generation-based fuzzing, you generate inputs from scratch. Maybe you're given a grammar or you're not, but inputs are generated from scratch. In mutation-based fuzzing, on the other hand, you have seed inputs, and then you mutate these seed inputs to generate other inputs. So we also formally link Shannon's entropy to the fuzzer's discovery rate. So discovery rate is a measure of the efficiency of a fuzzer, but it's parameterized in the number of tests that we've already generated. So discovery rate essentially measures the number of behaviors we expect to discover when we generate one more input. Of course, when you generate an input after we already generated 10,000 inputs, the number of behaviors we'll discover will be much lower. So we established this link between entropy and efficiency, and this is a very interesting theoretical insight, but we use this to our practical advantage. So our insight is that we only need to maximize information in order to increase the efficiency of a fuzzer. So we developed this entropy-based power schedule for Greybox fuzzing. So I explained that mutation-based fuzzing takes a seed as an input and then mutates that seed to generate further inputs. Now a power schedule simply chooses seeds from a corpus in a smart manner. The power schedule chooses seeds such that the inputs that are generated from that seed are more likely to discover new behaviors. And we develop an entropy-based power schedule, so our seeds that we choose are chosen such that they promise to really reveal more information about the behaviors of a program. So we develop practical estimators of information that are useful in fuzzing. And we also developed this open source implementation called Entropic. And what's so interesting about this open source implementation is that once we got some preliminary results, we sent the implementation and these results to Google, who is developing LibFuzzer, into which Entropic was integrated. And they conducted their own independent evaluation and found Entropic to be efficient indeed, and invited us to integrate this into mainline LibFuzzer. So in the beginning, Entropic was only enabled as an experimental option, but now it's just recently it's enabled by default, which means we could turn some theoretical insight into something practically really useful, because LibFuzzer, and now Entropic integrated into LibFuzzer, powers large continuous fuzzing platforms at Google and Microsoft. Okay, so let's talk about this statistical model for fuzzing. So I don't want to go into the technical details of the statistical framework, but what's important to mention is that each input can belong to one species. Now, a species is simply an abstraction. So earlier I was saying that you can execute an input and see the behavior of the program for the input. Behavior is another way of saying species. And behavior itself is also only an abstraction. So suppose an abstraction for discrete program property that you're interested in. You could also say the species for an input are the statements that an input executes, the branches that an input executes, the path that an input executes, and so on. Just to summarize this and abstract this, we call that as a species. So an input can belong to one or more species. And the next important concept is that of a species distribution. So some species are rare and some species are really abundant. So execute an input. Some statements, if my species is a statement, are almost always executed. Like the first statement in a program is always executed. It's an abundant species. But then there are very rare species. The probability that your fuzzer generates an input that belongs to that species is very low. Right? So the probability distribution over these species is called a species distribution. So now how can we compute the expected number of species discovered over time, or the number of behaviors we see as we generate more inputs? So it's actually very simple. You take the probability that you have not discovered a species after executing n inputs, and then take the complement to compute the probability that this species has been discovered after executing n inputs. And take this as a sum over all species. That's a species discovery curve. But there's also the discovery rate. It's simply the number of species you have discovered after executing n+1 inputs minus the number of species you have discovered after executing n inputs. So essentially the difference. Just to visualize this for you, this is the species discovery curve, number of species discovered over time. In the beginning, you discover a lot of species. Later, because you have already discovered a lot of species, you kind of degrade, discovery rate decreases. And discovery rate is essentially this difference. Okay, so now we switch to information theory. So this is an urn. We want to learn about the colors of the balls in an urn by sampling. We don't know the colors, we don't know how many colors there are, but we can sample with replacement from an urn. So here we have the distribution to sample a white ball is 3/4, and to sample a black ball is 1/4. Now information is computed like this. You take minus the logarithm of the probability to sample a white ball. That gives you the information for sampling a white ball. And the same for a black ball. Now, it's not important why it's a logarithm and whether it's a natural logarithm or any other logarithm. What's important is that this function is monotonically decreasing in p. So as we increase the probability, the information will be decreasing. It's also important that this quantity is always positive. And if there's a probability 1, there's no information, right? If I draw a ball from an urn and I always see a white ball, there's no information I gain from drawing that white ball. So why is information for white balls slower than for a black ball? Because when I just randomly draw a ball, I'm not going to be surprised to draw a white ball here because it just happens very often. But if I draw a black ball, I'm going to be more surprised. So there's more information in drawing a black ball. And the average information from each draw is called entropy. So now here's another urn. All colors are uniformly distributed, which means there are as many white balls as there are black balls. And for this uniform distribution, entropy is maximized. So entropy is higher. Again, the quantity itself doesn't matter, but it matters that this is higher than this. Another property is that the information that you learn from two independent events is the sum of the information you learn from each event. So here we have three colors and a non-uniform distribution. And we see that information is even higher, simply because you'll be very surprised to draw another color. So that's the key idea behind information theory. Now we kind of link fuzzer efficiency to entropy. And we do this by factoring out discovery rate into this formula. It's simply working out these formula. And then through some Taylor expansion and some smart manipulation, derive this formula. We can see that entropy is nothing but the discovery rate of an infinite fuzzing campaign where we generate infinitely many test cases. And if you have a steeper curve in the beginning, efficiency will be higher. That's the key idea, right? So fuzzing efficiency is an information theoretic quantity. Now, how can we use this? We increase Shannon's entropy, then you increase fuzzing efficiency. So, as I said, in Greybox fuzzing, we have a seed corpus. And we can have a power schedule, which assigns a probability to sample that seed and fuzz that seed. Or you can also say the time you spend fuzzing that seed. That's called energy. And you assign more energy to a seed that promises to reveal more information. That's the key idea of our power schedule. Now, that's what we use for boosting Greybox fuzzing. But we have to tackle a few challenges first. Entropy is defined in the multinomial model, which means that each input can belong to only one species. What do we do if an input belongs to multiple species? Like an input executes multiple statements. Well, it's been suggested in literature that in this case, you normalize the sampling probabilities. So you choose a p prime such that p prime is the original entropy divided by the sum of all probabilities. Now, because we can have multiple species, this doesn't need to be sum up to 1. In the multinomial model, this would sum up to 1. So, okay, you normalize. Technically, we don't have the average information anymore, but it still maintains the properties of entropy. So now, how do we compute the local entropy for a seed? Maybe know how to compute the global entropy for the entire fuzzer. How to do that for a seed? So we simply define something called a local species distribution. Fuzzing that seed, we observe the species that we see in the neighborhood of that seed, and then compute a probability for these species. That's called the local species distribution. And now local entropy is simply plugging in this local species distribution into the entropy formula. So now, okay, we know how to compute local entropy, but we don't know the local species distribution, right? You have a new seed, you have never fuzzed that seed. What is the entropy for that seed? We don't know, but we can estimate. What we can do is we can fuzz that seed and just observe, count the number of times we see each species in the neighborhood of that seed. And this count is called incidence frequency. Plug this into a formula of entropy, and we get the plug-in estimator or maximum likelihood estimator. But turns out that this maximum likelihood estimator severely underestimates. Very simply, you have never fuzzed a seed, your incidence frequencies will be 0. This entropy will be 0. You will never assign any energy to that seed, so it will never be fuzzed. We don't want that. So how do we overcome this problem? We take a Bayesian approach. So in the Bayesian approach, we already know that entropy is maximal for the uniform distribution, right? If each species is equiprobable. Now, for a newly added seed, we simply assume an uninformative prior in Bayesian speak over this local distribution, which means all probabilities are equal. In order to achieve this, we use the beta distribution, and specifically the mean of that beta distribution, which is also called a Laplace estimate. So you add 1 to each incidence frequency. That's the simple trick. It's also called add 1 smoothing. And now you get probabilities for a seed that has never been fuzzed, that are equiprobable. And you plug this into our formula for entropy, and you get a new estimator. That's the estimator that we use for entropic. Now, this is the entire algorithm. So how does this work in a general Greybox fuzzing procedure? You're starting with a program P and an initial seed corpus C. And then you loop until there's a timeout. And you do the following loop. Firstly, you compute this energy. You estimate, for each seed that you have in your corpus, you estimate the entropy, the information that this seed reveals over the species in the neighborhood of that seed. You normalize and you assign that as the energy for that seed, which means higher information, higher energy. And then you take the normal fuzzing loop, the normal Greybox fuzzing loop, you choose according to that energy, mutate that seed, see whether it crashes. If it crashes, you report it. If it increases coverage, you add it to the seed corpus. But you also maintain these incidence frequencies. So, and now I'm going to hand over to Valentin, who's going to talk about the experiments.
Thanks, Marcel. Hi, I'm Valentin. I'm going to present the experiments we did on entropic. So the first thing is, as we said at the beginning of the presentation, entropic implementation is based on Fuzzer. So for the experiments, we're going to go entropic with Fuzzer. We evaluated entropic on 2 benchmarks, the Fuzzer test suite on OSS Fuzz. Both are benchmarked made by Google. The first one is a benchmark made with the intent of measuring Fuzzers, and OSS Fuzz is a more real-world, more realistic benchmark that Google runs every day on open source softwares. To make sure our experiments are significant, we run each experiment several times, which makes in total almost 2 years of CPU time. The first experiment we did is to measure coverage, to compare coverage between entropic and Fuzzer on the Fuzzer test suite. Here, which is 12 subjects, which we run each 40 times 1 hour. And the result is a resounding win for entropic, since entropic covers more branches than Fuzzer on all subjects. Then the other experiment, we also look at the coverage on OSS Fuzz. Here, as I say, it's a more realistic, more massive benchmark with 263 subjects, which we run each 4 times for 6 hours. Here, entropics cover more branches than Fuzzer on 77% of the subjects. On the top figure, you can see entropic, what's the difference of coverage. And you can see, for example, here on a quarter of the subjects, entropic cover 10% more branches. And on the bottom figure, here it says not only entropic cover more branches, but it cover more branches faster than Fuzzer. For example, on half the subjects, entropic cover the same coverage than Fuzzer in 6 hours in only 3 hours, meaning that on other subjects, entropic is twice as fast as Fuzzer. Finally, not only we look at the coverage, we also look at the crashes, which is kind of the bottom line of Fuzzer. And here, entropic find more crashes again than Fuzzer, and it finds more crashes quicker. Here, the line is below, the line of entropic is below, the dotted line, because entropic finds those crashes faster. So that's it for the experiment, and I'm going to hand over to Marcel.
Thanks, Valentin. In the spirit of open science and reproducibility, we make all of our scripts and experimental data publicly available. We also provide detailed instructions to reproduce our results. We feel that our approach to open science, open source, open benchmarking, using Google's FuzzBench, for instance, and open discourse facilitated this industry adoption. And we strongly believe that this openness is a reasonable pathway for sound and rapid advances in the field, and to facilitate effective engagement between both industry and academia. So what we did today is we explained how information theory can be linked and explain phenomena in software testing, and specifically in fuzzing. We have explained how we can turn this insight into our practical advantage and boost Greybox fuzzing using this information theoretic approach. We provided some empirical evidence that this approach is effective, and we provide all our artifacts for the research community to reproduce our results. Thank you.